Okay, now we're going to be looking at section 5.1 on Eulerian graphs, named after the Swiss mathematician Leonhard Euler. Now, you've already done a little bit of this in a video. You've looked at the Königsberg bridge problem. Okay. So some of this is going to be a review. You may already have an understanding of the topics we're doing in this section, or know the statements of the proofs. You may not have seen the proofs of these two theorems here. Okay, so just a little review. An Euler path. This is a path that includes every edge exactly once. Okay, so it must include all the edges exactly once. You don't walk over any edge twice when you're going on this path. Of course, an Euler circuit would be a closed Euler path. Okay. And we say that a graph is Eulerian if it contains an Euler circuit. Okay. Now, Leonhard Euler was a Swiss mathematician that first looked at these, looking at the Königsberg bridge problem, and put it aside for a while. Didn't think it was very important, but then went on to solve the problem. Okay. Euler, I have a little list over here. Euler directed the research. He was the advisor for the mathematician Joseph Louis Lagrange. Okay. Lagrange was the advisor for the mathematician Simeon Didas Poisson. Poisson advised Michel Charles. He advised H.A. Newton. H.A. Newton was the doctoral advisor for E.H. Moore. E.H. Moore was the PhD advisor for R.L. Moore. R.L. Moore was the PhD advisor for R.D. Anderson. One of R.D. Anderson's PhD students, doctoral students, was Tom Chapman. One of Tom Chapman's doctoral students was Bruce Hughes. And Bruce Hughes's first doctoral student was me. So I am a direct descendant, mathematically speaking, of Leonhard Euler. And I'm sure you can tell that the genius still lives on in me, of course. Anyway, that's a neat little thing. If you ever have a mathematician in mind, a professor somewhere, there is a website called the Mathematics Genealogy Project. And you can look at someone and trace their mathematics ancestry and descendants as well. Okay, we have two theorems in this section that are very easy to understand. Unfortunately, the first one here is a little bit long to prove, but, and you may already know it, as I said, a connected graph that has no loops is Eulerian if and only if the degree of each vertex is even. So let's do a proof here. And we'll do the only if part first. So we're going to assume here G is Eulerian. Now, some people do not capitalize this, but I think if it's still it refers to a proper name, so I think it ought to be. Okay. So if G is Eulerian, then there is an Euler circuit in G. There is, and this, there is Okay, and it leaves as a vertex as many times as it enters. Okay, if it leaves a vertex as many times as it enters, then that means that each vertex is of even degree. Okay, now the other direction is a bit harder. Okay, so in this case, we're going to start with all even degree vertices and show that this is an Eulerian graph. We're actually going to come up with a technique for finding one here. So let's suppose G is connected and every vertex has even degree. Okay. So as I said, I'm going to construct an Euler circuit in here. So let's start with any vertex. And let's give it a name, V, say. Okay, comma. And traverse some sort of, okay, and just kind of in any way you want to. Let me clean this up a little bit. Any way you want to traverse distinct edges until you return to V. Now you won't get stuck anywhere else because anytime you enter a vertex, since it's even degree, there's a way out. So you'll be able to do this. Okay, now we're going to get a circuit here. Let's give this guy a name, C1. This circuit. Okay. Now, if it includes all the edges, you're done. We're done. Okay. So if we make some sort of circuit, we're guaranteed to be able to get back to V somehow, and we're done if it includes all the edges. Okay. Otherwise, okay, let us form a subgraph. I'm going to call this H1 by deleting this circuit we just constructed and any resulting. Okay, you may have some vertices that are just kind of sitting out by themselves. So any resulting degree 0 vertices. Now the book says something to the effect that you'll get a connected subgraph H1. Well, you don't necessarily get a connected subgraph, and I'm going to do an example where you don't. But the resulting subgraph will have components. It will have some connected pieces. Okay. So H1 will have at least one component because it might just be okay. That is connected subgraph here, where all of the vertices are even degree. Okay. What I should say here is have components where all the vertices are even degree. And with the understanding that H1 itself might be just one component. Okay. I didn't want to imply that you might have one component that's even degree and others won't have even degree vertices. Okay, so what we want to do we know that since G was connected, since the original graph was connected, okay, then at least one of the there is at least one vertex in H1, okay, will be a vertex in C1. Okay. So, in other words, when you traverse this original circuit, at one point it will have gone through a vertex in my subgraph here. Let's call this vertex. Oh, let's give it a name. Let's call it U. Okay, so U is a vertex in my subgraph, and it was also a vertex in the circuit we first built. Okay, now U is in some component of H1 where all the vertices will have even degrees. So what we're going to do is to, in H1, okay, let us construct a circuit starting at U. Okay. In the same way that we did C1. Let me back up a little bit here. In H1, okay, start at U and traverse distinct edges. Until you return to U. I should say until we return to U. Well, so you return. Okay. This gives us a new circuit. You can't read that at all. Sorry about this. I need to screw things up a little bit. Let's call it C2, say. Okay. Okay. Now, go back to the graph G. In the original graph G, append, okay. Append the C1, the C2 circuit to C1. At the vertex U. Okay. This gives us a new circuit. So it's a new circuit. Okay. Which in the original graph, okay, does this contain all of the edges? If this contains all edges, we're done. Okay. If not, repeat, form a new subgraph. H2 by deleting, let me call this guy C3. C3, etc. Keep this up until you're done. Keep this up until well, I can't write. I can't write because I can't see what I'm doing. Keep up this process until we have a circuit that is an Euler circuit. Okay. I don't know where you can read that. Let's see if we can make any sense out of it by looking at an example. And this is an example that's done in the book, but I'm not going to really do it their way. Here is a graph. It is a connected graph where every vertex has let's do it. Every vertex has degree 2. All right. Now, we want to construct an Euler circuit for this. So the thing is, start with any vertex and traverse distinct edges until you return to that vertex. So I'm going to start at 5. Okay. And I'm going to go 5 to 6 to 5 to 3 to 2 to 5 to 4 and back again. Boy, this is hard to do. 2 to 5 to 4 and back again. So let me write this thing down here. This is my C1. It is 5, 6, 5, 3, 2, 5, 4, 5. Okay, now what we do next is to throw out that graph, that circuit. Okay, then we'll be left with 1, 2, 3, 4, 5, 6. Okay, so we have this left. So we throw out circuit C1, but we also throw out the degree 0 vertex that we had. Okay, so this is my subgraph here. This is H1. Okay, now I have two distinct components here, and so I'm going to take a look at this component on the right that includes 3 and 6. Okay, it has components where all the vertices are even degree, and at least one of the vertex in H1 will be a vertex in C. Okay, so I'm looking here at this component 3, 6, and it has a vertex in C, say 3. Okay, so initially let's go back up here. Get my little pardon me, this is okay. Okay, I said V was equal to 5. Okay, now I'm going to go down here, and I'm going to have in H1, I'm going to have a vertex U, which is going to be 3, and my circuit here is going to go 3 to 6 to 3. So I have a circuit here, which is 3, 6, 3. Okay, so now let's go back to my original graph. And what we want to do is we want to append this circuit into the original circuit. In other words, I take 3, 6, 3, and I replace, go back to the original here. Go to the original and stick it in. So I'll have my new circuit will be, will be 5, 6, 5. I'm sorry, I can't see what's going on here. Okay, hold on a second. Okay, so my new circuit, which I'm calling C3, is 5, 6, 5. Instead of 3, I have 3, 6, 3, 5, 4, 2, 5, 4, 5. So 5, 6, 5, 3, 6, 3, 2, 5, 4, 5. Okay. Now, go through the process again. Throw this circuit out, and what we're left with is an H2, which just consists of the vertices 1. What's going on here? 1, 2, and 4. I'm having trouble because every time I drop something, my can't see the cursor. Okay, 1, 2, and 4. Okay, so what we do here is we construct a circuit in this subgraph, and using a vertex that connects that is part of the previous circuit. So it's going to be, I can use either a 2 or a 4, but I'm going to use a 2. So I'm going to do 2, 1, 4, 2. Okay. So I'm going to go around the circuit in a counterclockwise way. And we take this guy then and put it in here for the vertex 2. And so the circuit we end up with, and you're just going to have to is 5, 6, 5, 3, 6, 3. That's the piece we added 2 in there. And instead of a 2, I put 2, 1, 4, 2, and then 5, 4, 5. Okay. This gives me an Euler circuit for my graph here. Okay. All right, now we want to look at theorem 5.1.2, which is a fairly straightforward theorem. My proof is a little bit shorter than the books does. It says a connected non-Eulerian graph, so that means it doesn't have a circuit. Okay. But let's say we have connected non-Eulerian or Eulerian graph with no loops, has an Euler path if and only if it has exactly 2 odd vertices. Okay, so let's see what we can do here. And again, I don't know why the cursor keeps getting lost. Okay, so the only if part, this way, so we have an Euler path, we need to prove that it has exactly 2 odd vertices. If G has a path from, say, from U to V, then this path passes through every other vertex and includes each edge exactly once. Okay, so in other words, it has to go through every vertex. Right? And it includes every edge, so it can't stop in any of the other vertices. So the other vertices must be of even degree. Furthermore, U and V must be odd, or else you wouldn't be able to stop in one of them or start in the other. Start or stop. Then we would just pass through. Okay, so that direction is pretty easy. This other direction is not too bad either. The book has a longer proof, and I've looked at it and not real sure why he uses such a long proof. Okay, it looks to me like there's a short one. So if you can spot a mistake in my proof, then please let me know. So we'll do the other direction. So let's suppose we have a connected graph with 2 odd vertices. let's give them some names. Say U and V. Okay, now construct a new edge joining U and V. Let's call this E, say. Okay, now the new graph let's call this G prime, which is my graph G union with this edge E. Okay, okay, it is a connected. Okay, and every vertex is an even degree. So by the previous theorem, there is an Euler circuit. Okay. G prime. Now this Euler circuit, of course, must include every edge. So we have U and V, and we have the rest of the stuff going around here. So in other words, E is in the Euler circuit. Okay. Take this edge away. Remove E, and we have U to V. I mean, we take that out. We don't have a circuit anymore. What we now have is an Euler path. From U to V. Okay, done. Okay, that's all we're going to cover in section 1. We're going to skip section 2. I will have section 3, 4, and 5 done fairly soon. They're pretty short as well.